2. Motion of a falling object. The purpose of this lab was to compare the motion of an object that falls from rest compared to a model with drag and without drag. It assumed motion only in the y direction. It was based on the physical concepts of Newton's second law, which is also known as the momentum principle, which means that F net equals delta p over delta t. It was also based on the velocity update formula and the position update formula. This was also based on the gravitational force, which is negative mg in the y direction, the magnitude of gravity, which equals gmm over r squared, and the acceleration due to gravity on Earth, which equaled a constant of 9.8 meters per second squared. This was the free body diagram, where the drag force increased as the magnitude of velocity increased. This is because the drag force equals b times magnitude of velocity squared in the y direction, in the positive y direction, which is opposite the gravitational force. The main result was that the lab was that the experimental tracker increased position at a slower rate towards the end due to the drag force in the opposite direction. The model with drag was closer to the experimental, but it was still a bit off due to external factors, which I'll talk about later. The system was the paper and the surroundings was everything else. This was the tracker experimental model, and that's how the position versus time was tracked. These were the initial conditions of 0 in the position, velocity, and time, and the final position was negative 1.05 meters, and the final time was 0.5 seconds. The video seconds per frame was 0.033 seconds, and the paper mass was 0.0293 kilograms. This was the computational model without drag initial conditions in code. These were the equations to code, so the net force was equal to negative mg in the y direction, and the velocity update and position update formula. This was the computational model without drag for the iteration, so this is how the velocity was updated and the position was updated and the clock was advanced. These were the initial conditions for the computational model with drag, and the main difference was the proportionality constant 0.0019, which was determined experimentally through the computational model. And these were the equations to code, so also the drag force was added and it was computed here by putting this formula into here. These were the graphs of position versus time comparing the model without drag force and the model with drag force. So you can see the model without drag force increased position at a faster time, increased position at a faster rate towards the end. And these are the experimental compared to the computational models on one graph. So the experimental was red, and so you can see how the computational increased position at a faster rate towards the end, especially the model without drag. The model with drag was a little less, but it was still some discrepancies, which I'll talk about, due to possible sources of error. There was differences between the predicted and computational model without drag, so the final y position started to differ around 3 seconds. It increased faster for the computational model since it did not consider an upwards drag force. The difference between the computational model with drag was it was a better estimate of the drag force of constant b equals 0.0019 in the positive y direction. Both models increased position at a faster rate towards the end due to possible sources of error, including errors in the tracker position analysis, error in placement of the center of mass. It didn't account for motion in other directions, and inaccuracy to determine the drag coefficient b. So, which models, if any, predict a terminal velocity, which means that net force is 0. This is the computational model with drag. It did predict a terminal velocity. You can see how the velocity started to level out and become a constant towards the end with the asymptote of negative 3.4 meters per second, which was the terminal velocity. So the model with drag predicted a terminal velocity. Imagine that an object was initially thrown downward with an initial velocity. Would the terminal velocity in this case be the same or different from the case where the object was initially dropped from rest? So I changed the initial velocity in the code to -1 in the y direction just to test this out, and the asymptote did reach at an earlier time. So it reached a terminal velocity at an earlier time, but the terminal velocity was still constant around -3.4 meters per second. So you can see that the terminal velocity in this case would be the same. Thank you.